Hi everyone, I'm Mark, and I'll be talking about my project, which is search for baryon number violation in Belle data, which relates to particle physics analysis, in particular mine, using data collected in Japan with the Belle collaboration. Okay, so as an introduction, during the Big Bang, everything produced should have been done so in equal and opposite quantities, just like simple energy conservation. Matter abides by these rules, so it really is a quandary in physics currently why our universe consists of so much more matter than antimatter, as they should have been produced equally. So, in order to try to understand this, my project takes one of the avenues in which this could possibly be explained. However, currently there is no physical evidence to explain such. There are a few theories and propositions, and my project attempts to search essentially for physical data of one of these propositions, and this is essential just to understanding more about the natural world and our beginnings, and henceforth, just more about us in general. So theoretical backing. In 1967, Sakharov proposed three conditions for baryogenesis, which is the same as asymmetry between matter and antimatter. And his conditions are baryon number violation, C and CP violation, and departure from thermal chemical equilibrium. So C and CP violation, some has been found to exist. I'm not going to talk so much about that. Um, my project focuses more on baryon number violation, as the Big Bang clearly has the result of departure from thermal and chemical equilibrium. However, for baryon number violation, baryon number is essentially a quantity given to subatomic particles, so like a proton or a neutron, who have a baryon number of 1, whereas like an antiproton has a baryon number of -1. And during interactions, this normally should be conserved, but that is not always the case, and it's not as true of a conservation as, say, energy is. So one way to find baryon number violation is through baryon oscillations, which would be the avenue leading to figure out or finding instances of baryogenesis, which would help explain the asymmetry in matter and antimatter, and that is what my project seeks to do. So for my project, I am looking for a certain decay, which is shown on the right, which is decently complicated, and my goal is to try to find it in the Belle data and measure it. If I were to find such instances, the rate at which this charmed omega baryon oscillates. Baryons are just certain subatomic particles, and there are theoretical proposals that this charmed omega baryon in specific can oscillate on its own. If I am unable to find this, I will measure just an upper limit on the frequency which it occurs. So just based on the probability of not being able to find it, and all this amount of data will help me get a result nonetheless. I also include here on the bottom, this is a Feynman diagram detailing a decay of a B meson into omega sub c lambda bar, which are the two baryons which I'm looking at, just to show that it is theoretically possible this can occur, even though the rate is probably very slim. Okay, so my project, as I mentioned previously, I will be using data from the Belle collaboration or the Belle Detector. You can use either interchangeably, which is a detector in Japan. The way this particle detector works is it fires an electron against a positron, or like the antimatter equivalent of an electron, and that annihilation produces just various rare particles. In my case, well, specifically, I'll be looking at the BB bar meson pairs which are produced, which again are just certain particles that result from this annihilation. They are graded in pairs just to conserve charge, as well as other quantities. And there are about 772 million of these so far, so there is a chance I will be able to find my decay in the data. However, this detector is only physically able to record final state particles in the events. So whatever actually hits the detector, for instance, in my decay chain, it'll only be, for instance, the protons, the pions, this kaon. And so it is my job essentially to reconstruct this chain otherwise. And that is essentially what I do. So my methodology is I have an algorithm which can sort through all of this data and reconstruct the event. So I start from the proton and the pion. I create lambda, et cetera, for all the particles up to my B meson candidate for each event that I'm looking through. The way I do this is by testing it on what is known as Monte Carlo data samples, which is colloquially fake data because it is computer generated using everything that we know about the modern world, and it just helps to refine the process, especially for instance because my decay that I'm looking at is probably very rare and won't happen very frequently. So being able to generate data that results in that decay more often is very useful, just again for refining the data analysis. And then once my methods and everything I write up is approved, I can go into looking at the actual data and finding those numbers. So I've made a lot of distributions, and it'd be very hard to try to talk about everything I've done, but I just have a few that I'd like to highlight just to show a little bit of a glimpse of what some things are that I do. So on the top left and right, we have fittings of two quantities which are in every single event or like certain decay I'm looking at. They are known as delta E and beam constrained beam mass. They're the two most important quantities when it comes to judging how good of a certain decay is or how likely it is to be one of ours that we want to look at. Delta E is the change in energy from the beginning of the interaction to the end. So from that annihilation of the electron positron to the final state particles. And then beam constrained beam mass is how we, or precisely what the mass is of our B candidate for each of those decays, or essentially what this B meson is. So here I am doing some curve fitting, which helps you to better understand the distributions as well as the probability of what I will find in the actual data once I look at it, because here I'm only looking at signal MC. Specifically, I'm fitting with Gaussian curves, which I mentioned up here. This one is the product of two Gaussians. This is a singular one. On the bottom left, we can see a two-dimensional distribution of both beam constrained beam mass and delta E. Again, this is using fake data, so the signal looks very good, and essentially we have all events which match our decay, so it is confined to this very small box, which is about 95% of the sample. And then on the right, I also include just an interesting plot, which I had worked on to better understand how antiprotons interact with the detector itself, which, if you are interested, it is essentially I'm color coding if we were able to properly reconstruct that antiproton or that event because of that antiproton. So there are two divots, which I found to be very important and looked into further. I also include, just because I have not looked into actual data yet, I don't have my final true conclusions, just an estimation of what I hope to find. So I include decays, which are part of this chain, and am able to calculate that. Hopefully, I'll be able to see about 26 events. And the actual data from the 772 million pairs, this is a very conservative number, and hopefully it'll be higher, but that's still very promising. Okay, and so that's really all I have is an overview. I do have future plans, which are introducing a new decay into the analysis. This was brought up at the last meeting, where it is possible that I can include a whole new decay chain that's very similar to my own, but slightly different with a few of the particles. And that would help me find, or give me the chance to find another avenue for oscillations. This is known as a starred charmed omega baryon, which is interesting. Essentially, you consider it as an omega baryon, but like charged with a photon or a higher energy level. So that also is a chain which has a chance to decay, and I'm looking to that as well. Once I'm finished with that, I can document my work, request a committee to look further or to look into the actual data. At that point, hopefully I can write a paper to be published. And thank you, that's all I have.